Carbon dioxide is itself not put into the atmosphere by fossil fuel burning. The oxygen of the carbon dioxide is already present in the atmosphere. What's added is carbon and hydrogen atoms primarily. So when you combine carbon with oxygen in the atmosphere to make carbon dioxide, you're mostly using mass that's already there. Carbon dioxide has a very low concentration in the atmosphere for a reason. The Earth has an appetite for it, essentially wants to eat it, use it as fuel, as a means of storing solar energy, and, in terms of living things, making skeletons and tissues, which can then get incorporated back into the crust. It's like going out and handing out free gasoline to people, saying, here's an energy source, take all you want. Naturally, the abundance of gasoline would tend to drop under those conditions. Nature abhors free, unused energy. If there's an energy supply, something living, if it's present, will try to use it up. So the concentration of carbon dioxide is very low in the atmosphere for a reason. And if you try to thicken the atmosphere by pouring out more carbon, you're really on a treadmill. It's very hard to get ahead that way. Carbon dioxide can fall out of the atmosphere as a component of rain. Rain is naturally acidic. It tends to have a pH around the low 5s or so, without adding any extra acids that we call acid rain components, like nitric acid or sulfuric acid. Carbon dioxide will combine with water to form carbonic acid, a naturally weak acid, and that is what we call rain. Rain is a carbonic acid solution, carbon dioxide plus water. So when you combine the two in the atmosphere, carbon dioxide can drop out again quite quickly, just as quickly as water can. And also, when you burn things like natural gas and other hydrocarbons, one of the main things you get from the combustion, particularly from natural gas, is water, because natural gas, methane, is 1 atom of carbon and 4 atoms of hydrogen. When you burn that hydrogen, it combines with oxygen in the air to form water. When you burn roughly equal amounts of coal, that's carbon, and methane, which is carbon plus 4 hydrogen atoms, you get carbon dioxide and water in equal proportions, and then they can wash out of the atmosphere right away.
One way to express the speed at which carbon cycles in and out of the atmosphere is to figure out the fraction of the atomic weight of rain that is carbon and multiply that out by the yearly rainfall and snowfall that occurs over the continents. This works out to something like over 20,000 billion tons per year. And in the tropics, where most of the sunshine strikes and most of the evaporation occurs, and you get some of the biggest dumps of rain, most of the area of the Earth is ocean, over around 80% of it in the tropics. So I think it's reasonable to say that of the world's rainfall total on land, at least that much, again, falls over the oceans. So a reasonable assumption, I think, is doubling the land total, which would give a total carbon rainfall in the neighborhood of 40,000 billion tons per year. That would be enough if you could stack the carbon up in a pile with straight sides to make a pile 1 kilometer wide, 1 kilometer tall, that would wrap all the way around the planet. Or expressed another way, compared to the 10 billion tons of carbon that people are believed to put out, it's about 4,000 times as much. Water and carbon dioxide are the means by which the Earth offsets any attempt to change its temperature. They're the means by which the Earth regulates its temperature. The amount of evaporation and precipitation of water and carbon dioxide that occurs each year has got to be at least 200,000 cubic kilometers worth for the Earth. Now, anybody who's gone hiking and tried to haul water around, ignoring for the moment that you're mostly made up of water and carbon compounds in your body, knows how much effort it takes to lift that stuff. And the Earth is pushing up all that water and carbon dioxide against the force of gravity, and pulling it all back down again against the force of friction. All that requires work. In the physical sense, the energy for that work can come only from heat. If you have heat in a system, you draw on that heat to do the work. The amount of work done is equal to the amount of heat lost. So, if you do work, you are consuming heat, not producing it. Water and carbon dioxide are the things the Earth uses to consume heat. So the more of it that's put out there, the more heating is being cancelled out.